welcome to lecture number 37 of fuzzy sets, logic and systems and applications. In this lecture, we will discuss properties of composition of fuzzy relations. As we already know that the composition of fuzzy relations are based on the either max min criteria or max product criteria. And here I would like to mention that the fuzzy relation R, fuzzy relation S1, fuzzy relation S2 and fuzzy relation T are the fuzzy relations that are defined on spaces, that means the universe of discourses X cross Y, Y cross Z, Y cross Z and Z cross W respectively. So, this means that the relation R, which is here, this relation R is defined in the universe of capital X cross capital Y. Similarly, S1 and S2 are defined in the universe of discourses Y cross Z. T is defined in the universe of discourse Z cross W. So, as I have already mentioned that R, S1, S2 and T are fuzzy relations, and we have already discussed the composition of fuzzy relations in the previous lecture. So, here we will be discussing as to how these composition of fuzzy relations hold these properties. So, first property is the associativity, then the second property is distributivity over union, and then we have weak distributivity over intersection. And finally, we have monotonicity. And all these properties are defined here in this column, where we have the composition of R and S1. So, when we say composition, this composition can be either max min or max product. So, the composition of R and S1, and then whatever we get here out of this R composition S1, and then when we further compose this with T, we are going to get the composition of R and the composition of S1 and T. So, these things must be understood very clearly, that the associativity with respect to the composition is satisfied, or in other words we can say that the composition of fuzzy relations R, S1 and T are holding good with respect to the composition. Similarly, distributivity over union. So, we see here that we have a composition here, and please understand this small o is for the composition, this is a symbol for composition. So, we have small o, so R is small o, and then we have the composition of R and S1 union S2. So, this can also be written as, or in other words we can say this is equal to the union of R composition S1 and R composition S2. Similarly, the other property, the third one, the third property is weak distributivity over intersection. So, here we have the composition of R and the intersection of S1 and S2, and this is going to be either the subset or equal to the intersection of R composition S1 and R composition S2. Similarly, here we have the fourth property, that is monotonicity, and here if we take S1 and S2 fuzzy relations, and S1 is the subset of S2. So, then in that case the composition of R and S1 will be the subset of R, composition of R and S2. So, this is called the monotonicity here. And as I have already mentioned that this small o represents the composition symbol, and this composition can either be the max min or max product. So, let us go through these properties one by one, and as I have already mentioned here that for fuzzy relations R, S1 and T, this relation, this is associativity relation, this holds good. And I have already mentioned about R also. R is defined in the universe of discourse X cross Y. Similarly, S1 is defined in the universe of discourse Y cross Z, and T here is defined in the universe of discourse Z cross W. So, this needs to be understood very clearly, and this is called the associativity property for composition of fuzzy relations. So, this means that we have our composition S1 and then whole of it composed with T is going to be equal to the composition of R and the composition of S1 and T. So, this is what this means, and this is called the associativity property. So, let us take an example to understand this better with respect to the fuzzy relations. So, let us understand this associativity for composition of fuzzy relations. So, here we have taken the fuzzy relation R first, we see here this is R fuzzy relation, and then we have another fuzzy relation here as S1, and then we have the third one is the fuzzy relation T. And we clearly see that R is defined in the universe of discourse capital X cross Y. Similarly, S1 is defined in the universe of discourse Y cross Z, and here T is defined in the universe of discourse Z cross W. So, let us now compose R and S1 first. We already have done this exercise in the previous lecture. So, based on that we will try to generate the composition matrix. So, we have the composition of R and S1, which is this, and this is going to be equal to all these elements, means we have 3 cross 3 elements here in this composition of fuzzy relation matrix. And here please understand that when we compose the fuzzy relations, so all these exercises must be inconversant with the order of the matrix. This means that we need to have the suitable order of the fuzzy relation matrices, that is needless to say. So, here now as I have already mentioned that we have followed this criteria for max min composition, max min composition. Here we could also follow max product if it is said. So, but in this case we will only be interested in max min. So, we have followed max min criteria, and based on this when we apply this criteria we get mu R O S1 X1 Z1 like this. We have already done this exercise in the previous lecture. So, I am not going to explain this again. If you have any doubt you can go through the previous lecture to understand this better. So, the max of all the mins here, and then when we take the max of these, the outcome of the mins, then we are going to get 1 here in this case. So, similarly all combinations of elements of our composition S1, we are going to get here this matrix R composition S1. So, you can just try this and you are going to get the composition of fuzzy relation matrix R and S1 here, which is 1, 0.7, 0.8, 0.5, 0.6, 0.8, 0.7, 0.7, 0.9. And this outcome is, again you can clearly see that is defined in the universe of discourse x cross z. So, we have now at this moment the composition of fuzzy relation R and fuzzy relation S1. Now, let us go further. So, this part is done here. So, now let us go further, and whatever is the outcome here is we compose with T. So, let us take T here, and when we compose this T with R composition S1. So, means we take first R composition S1 and then we compose it with T. So, both R composition S1 and T both are fuzzy relations, because composition of R and S1 is going to give us another fuzzy relation. So, here we compose these two here, and when we compose this, what we are going to get upon applying the max min criteria is this. So, R composition S1 and whatever is the outcome here is composed with T is going to give us a new fuzzy relation matrix, which is defined in the universe of discourse x cross W. So, this is what is the outcome out of this exercise. So, this is the LHS, I can say this is the LHS because left hand side is coming like this. Now, in the property, let us now try to find the RHS. So, we see that this is the RHS part and this is the LHS part. So, we have done LHS. Now, let us find the RHS part using the same set of fuzzy relation matrices. So, let us now find the S1 composition T. So, when we apply the max min criteria as we see here, with the same max min criteria, if we compose S1 and T, which is here, we get this matrix. So, we get a new fuzzy relation matrix which is defined in the universe of discourse of y cross W. Now, in the RHS, if we see, we have another fuzzy relation R with which this outcome needs to be composed. So, when we compose, when we take the composition of R and S1 OT. So, S1 OT we already have. Now, let us take R and make a composition of this and let us see what we are getting. So, here when we do that, we are getting this outcome, and we clearly see that we are getting a new fuzzy relation matrix out of these compositions, which is defined in the universe of discourse capital X cross W. So, this is nothing but the RHS part. So, when we write LHS here and RHS here, means both LHS and RHS here, we see that both the fuzzy relation matrices are same, are equal. So, we can say that the associativity property holds good for the composition of fuzzy relations. And with this example, we are able to understand that if we take any three fuzzy relations, and then when we apply the associativity property, so with either the max min or max product, this property is well satisfied, or in other words we can say that the associativity property for composition of fuzzy relations hold good. Now, the second property is the distributivity over union, and this is also for the composition of fuzzy relation. So, when we say composition of fuzzy relations, so this distributivity property over union is also holding good. And what is this? This is nothing but, if we have fuzzy relations R S1 and S2, and this R S1 S2 are defined in the universe of discourses as we have already discussed. So, in that case, this distributivity over union, we have the composition of R and the union of S1 and S2 is going to be equal to the composition of R and S1 and composition of R and S2. And if, since these two are equal, so we can say the distributivity property over union for composition of fuzzy relations hold good. So, this also let us understand properly by taking an example. So, here also we are taking fuzzy relations R S1 and S2. Again, these are defined on spaces x cross y, y cross z, y cross z respectively. So, means R is fuzzy relation set is defined in the universe of discourse capital X cross y, and S1 is defined in the universe of discourse capital Y cross z. Similarly, S2 is defined in the universe of discourse Y cross z. So, this way we see that we have R S1 and S2 as three fuzzy relation matrices. Now, let us try to see whether the distributivity over union property holds good for these fuzzy relations R S1 and S2. So, in this process we have first the LHS and then we have RHS, and let us move ahead. First take the LHS part. So, LHS is here, this is our LHS. So, for computing LHS we first need to find the union of S1 and S2. So, we already know how to find the union of S1 and S2. So, when we take the union of S1 and S2, we simply take the max of the corresponding membership values. So, when we do this exercise, we get here as union of S1 and S2. Now, I am writing just this is the matrix which is S1 union S2. So, when we take the composition of R and the union of S1 and S2 here, we get this as the outcome. So, this is nothing but the LHS part. So, this is my LHS part. Now, let us move ahead and we see that in the right hand side, the RHS, we have the union of two compositions. So, let us first find both the compositions. The first composition here is the composition of R and S1, which is this. This by applying the max min composition, as I said before that it depends. If you have been asked to find the R composition S1 by max product, then you can use the max product criteria, but here we are using the max min criteria. So, the outcome of R composition S1 is this, and then R composition S2 is this. Now, let us take the union of these two. So, when it comes to the union, then we apply the max criteria again and we take max of the corresponding membership values of the both fuzzy relations matrices. So, we see that here when we take the max criteria, which is this, then the outcome is this. So, this is nothing but the RHS part. So, this is the outcome of the union of the R composition S1 and R composition S2. So, then when we write the outcome of LHS and the outcome of RHS, we see that both of these, the fuzzy relation matrices that are the outcome of the composition R and S1 union S2 and the union of R composition S1 and R composition S2. So, both are same. So, in this way we can say the LHS is equal to RHS. So, this means that the matrices that we took, the fuzzy relation sets that we took holds good for the distributivity over union property. So, in other words we can say that the distributivity property over union holds good for the composition of fuzzy relations. And now, the next is the weak distributivity over intersection. So, when we have fuzzy relations R S1 and S2, and if we have the composition of R and the intersection of S1 and S2. So, if we have this thing, this is going to be the intersection of R composition S1 and R composition S2. This is called the weak distribution over intersection. So, what essentially we are doing here is that we are taking the intersection of the two composition in the right hand side. So, we first have the composition of two fuzzy relations, means the R composition S1 and R composition S2, we are taking the intersection of it here, and we have then the composition of R and intersection of S1 and S2. So, if we have this composition of R and intersection of S1 and S2, this is going to be the subset of the outcome of the RHS. So, let us take an example again to understand the weak distributivity over intersection again. So, here we have three fuzzy relation matrices R, S1 and S2, and again I would like to mention here that R is defined in the universe of discourse X cross Y, and S1 is defined in the universe of discourse Y cross Z, and S2 is also defined in the universe of discourse Y cross Z. So, let us now first take LHS here, and for LHS we have to have the composition of R and S1 intersection S2. So, let us first find this. So, let us first find the intersection of S1 and S2, and when we take intersection, we know that we use min criteria. We take min of the corresponding membership values from S1 and S2. So, when we do that, we are getting here this as the outcome. This is nothing but the intersection of S1 and S2. So, when we have this fuzzy relation matrix as S1 intersection S2, now let us take the max min composition of R and this matrix which is here. So, when we do that, so since we are using max min criteria, we are getting the final outcome as this, where the elements are 0.5, 0.6, 0.8, 0.5, 0.6, 0.2, 0.5, 0.6, 0.7. So, this way we get the LHS computed for our example using R, S1 and S2. Now, when we have LHS computed, let us now find the intersection of the composition of R and S1 and the composition of R and S2. So, here we have the composition of R with S1 and composition of R with S2. So, this is in the process of computing the LHS for finding RHS. So, let us now move ahead and see what we are getting. So, we see that our composition S1 is this, and this composition of course is again max min. Here also the composition is max min. So, we can quickly get the composition of R and S1 and the composition of R and S2. So, when we do that, then let us now take the intersection of these two. So, when we take the intersection of these two fuzzy relation matrices, since we are taking intersection, so we use the min criteria, the basic intersection. So, this can be found by taking the min of the respective membership values from both the fuzzy relation sets ROS1 and ROS2, and final outcome is here, and this is nothing but the RHS, which is the intersection of both the fuzzy relation sets. So, this way we have here the LHS and RHS. Now, if we see LHS and RHS both, we see that both of these fuzzy relation matrices are not same. We can clearly see that the LHS, which is the composition of R, and intersection of S1 and S2 has the elements 0.5, 0.6, 0.8, 0.5, 0.6, 0.2, 0.5, 0.6, 0.7. And similarly, when we see the corresponding elements in the case of RHS, where we have the intersection of R composition S1 and R composition S2, we see that we have 0.5, 0.6, 0.8, 0.5, 0.6, 0.5, 0.6, 0.6, 0.7. So, first of all, let me make it clear here that both of the fuzzy relation matrices of LHS and RHS, they are defined in the same universe of discourses. So, here the universe of discourse is X cross Z, and here also the X cross Z, the universe of discourse is X cross Z. And when we see the corresponding elements in the fuzzy relation matrices, so we see that the LHS, the each elements are either equal or lesser than that of the elements in the RHS fuzzy relation matrix. So, that means here we can say that the composition of R and the intersection of S1 and S2 is a subset of the intersection of R composition S1 and R composition S2. So, we see that each elements or every elements of LHS is either less or equal to the corresponding RHS fuzzy relation matrix. So, this way we can say that the fuzzy relation sets R S1 S2 holds good here, or we can say satisfy the weak distributivity over intersection criteria. So, in general we can say weak distributivity over intersection property is holding good for the composition of given fuzzy relations. Now, let us discuss the monotonicity as the other property, the fourth property here for fuzzy relations R S1 and S2. So, it is very simple in the sense that if we have S1 and S2 two fuzzy relations and S1 is a subset of S2. So, if this is the case, then the composition of R and S1 is going to be the subset of the composition of R S2, and this is called the monotonicity property. So, let us take an example similarly here, and let us see how the monotonicity property also is holding good for fuzzy relations. So, let us take the fuzzy relation set R S1 and S2, and here also we see that the universe of discourse for R is X cross Y. For S1 the universe of discourse is Y cross Z, and for S2 also the universe of discourse is Y cross Z. Now, let us choose S1 and S2 in such a way that our S1 is a subset of S2. So, if we choose S1 and S2 suitably, so that S1 is subset of S2, we can check here that each and every element of the S1 is either less or equal to the corresponding elements from S2. So, when we choose the S1 S2 fuzzy relation set like this, then let us now take the composition of S1 and S2 separately with R. So, here when we take the composition of R with S1, we find here a new fuzzy relation matrix, which is defined in the universe of discourse capital X cross Z. Similarly, when the fuzzy composition of R is taken with S2, again we have the outcome, and which is fuzzy relation in the universe of discourse X cross Z. Now, let us compare the composition of R and S1 and composition of R and S2. So, if we compare this with element wise, we see that all the elements of R composition S1 are either less or equal to the R composition S2, or in other words we can say that the elements of R composition S1 are either less or equal to the corresponding elements of the composition of R and S2, which is clearly shown here. So, this way we see that when we see that all this criteria, when we apply all the elements of R composition S1 are either less or equal to the respective elements of R composition S2, then we can say that the monotonicity property is verified for the composition of fuzzy relations. In other words, we can say the monotonicity property holds good for fuzzy relations, and especially with this condition that when S1 is a subset of S2 and when we take a composition either max min or max product like the composition of R and S1 and composition of R and S2, then the composition of R S1 is going to be the subset of the composition of R S2. So far we have used max min compositions of fuzzy relations to verify the properties in all the examples. However, on the same lines max product composition of fuzzy relations can also be taken. So, this way we have seen all the 4 properties with respect to the composition of fuzzy relations in today's class, and now in the next lecture we will study the fuzzy tolerance and equivalence relations. Thank you.